Now we're starting the session Planning, Navigation and Localization. The first paper is increasing the flexibility of the navigation algorithm for inertial pedestrian system by classifying motion type with support vector machines.
Good afternoon, dear colleagues. My name is Sekou Diane. I present the announced research paper, increasing the flexibility of the navigation algorithm for inertial pedestrian systems by classifying motion type with support vector machines. The research was done in Mira, Russian Technological University. The inertial navigation systems are known to have a wide range of applications in autonomous robots, in virtual reality, for audio guides in museums and etc., or for emergency missions where inertial models are mounted on the rescuers to assist their navigation in environments with low visibility. Thus, the inertial models are used in conditions where there is no access to GPS satellites, or there is no visible landmarks to orient by video. Inertial systems have a number of advantages because they can help to estimate the object's orientation and position between the moments of time where more precise coordinates are obtained from another navigation systems. But inertial models have also a number of disadvantages because it is known that they tend to accumulate the error with time. So one of the approaches to recover from this error is to use zero speed correction, and a number of methods are targeted to deal with this problem. For example, zero velocity update method, ZUPT, which allows to enhance precision of inertial model on a walking man or a walking robot by tracking the moments of time when the speed of this inertial model is close to zero. And combine it with extended Kalman filter, this approach allows to get rather precise measurements of object coordinates. So the disadvantages of this existing approach with zero update velocity method is tied lies in the problem that this method is tied to a specific type of movement. For example, the parameters obtained for walking people are not appropriate for tracking running people or tracking people climbing stairs. So the goal of our research was to make this method more adaptive and applicable for different types of motion which can be selected dynamically and in real time. And our method uses the widely known diagram of algorithm for inertial navigation, where primary inertial information undergoes integration, and the noisy navigation solution is refined with extended Kalman filter and with data from ZAPT detector to account for zero update velocity moments. But the refinement in our research considered the ZAPT detector module, and here it's shown in a bigger picture. We added to this module a support vector machine technology to distinguish between different types of movement. So support vector machine method takes as an input a time series of inertial measurements, and by classifying them into several types, it says which threshold ZAPT detector should use to understand that the zero time velocity moment has come. Here is, in the current slide, a formula for tracking the zero velocity moment is depicted. This formula says that zero velocity moment occurs under condition when the current acceleration of the inertial module is close to the acceleration of free falling g. And in the right part of the slide, experimental results are shown that the blue line is a echelon trajectory, and the red line is the trajectory obtained with our method, which is slightly differs from the echelon trajectory. Here is a picture of the mounting of the inertial module on the on the boot of one of our students, on the foot of one of our students, and in the right part of the slide, the picture is shown, which depicts the threshold estimation for different types of motion. For example, the dashed line corresponds to the normal walking, and the solid line corresponds to the running. So the thresholds for these two modes of locomotion is different, and the SVM method is used to dynamically switch between these two thresholds. And here are some results of the experiments. The first picture is where our student begins his motion. Then it proceeds his motion at the second time moment, at the third time moment, and so on. And here is at the final picture, final trajectory is depicted in the form of the number 8. Here is a video of the same process. The inertial module is mounted on his foot. So when he steps and the foot resides on the floor, at these moments the trajectory is corrected and refined. So this is the last slide. Thank you for your attention. Here are some introduction to support vector machines and results on the precision of our methods, which were 99% on our tested database. And also some results of the trajectories. Okay, thank you for your attention.
Thank you.
We reached our goal. The goal was reached.
Okay. Uh, Thank you for your presentation and questions.
I would like to ask a question, if you don't mind.
Yes, yes. Of course.
As I understand, you use cameras.
No, cameras were not used here. We use inertial modules. The device which has accelerometer and the gyroscope. We use this kind of.
Okay. Okay, and how many such modules do you use for one person?
For one person, we used just one module because we wanted to test the method. Although in the future several modules can be used to increase the precision due to the data fusion from several sensors, but we use just one.
Okay, thank you. Thank you.
Thank you for the question.